To understand computers, we use simplified models like FSMs, Turing machines, and RAM models. It's like trying to understand a car by looking at its blueprints. FSMs have states, transitions, and inputs, useful for traffic lights, vending machines, just like how you need to insert coins to get a snack. Abstract, computer, models. To understand computers, we use simplified models like FSMs, Turing machines, and RAM models. A Turing machine is an abstract computer that can compute anything, given enough time and memory. It's like a super smart robot that can solve any math problem, but it might take a while. The RAM model is a simplified view. Instructions act on registers in memory. It's like a game of chess, but with more bits and bytes. So now we have the turnstile example. So let me just draw this up real quickly. It's like trying to understand a car by looking at its blueprints. But don't worry, we won't make you draw the entire car, just the models. Just like how you need to insert coins to get a snack, and if you're lucky, you might even get a freebie. It's like a super smart robot. Don't worry, it won't get bored unless it's stuck in an infinite loop. And just like in chess, you need to think ahead or you'll get checkmated. Just the models. And if you get lost, just remember, it's not a bug, it's a feature. But don't try to hack the vending machine, that's just not cool. Don't worry, it won't get bored unless it's stuck in an infinite loop. And if it gets stuck, just restart it, like your computer. But don't worry, you won't lose your queen unless you're playing against a grandmaster. So now we basically have an example of turnstile, which is a type of a finite state machine. So the next topic is finite state machines. FSMs have states, transitions, and inputs. It's very useful for real world applications like traffic lights, vending machines, etc. We can take an example of an FSM. For example, we have here the turnstile example, right? So let's say there are two states, logged and unlogged. So first time when the user inserts the coin, what happens is the state changes from logged to unlogged, right? Now, when the user pushes the coin, now what happens is, again, the state comes back from unlocked to logged. Now, if there is a push, then it again changes back to locked. And here, if we put in a coin when it is unlocked, then it again changes to unlocked. So after pushing the coin, what happens is the state again changes from unlocked to again lock. So this is an example of what we call as a finite state machine. Here, logged and unlogged are basically what we call as states, right? So we have states. And then the next thing we have is what we call as transitions. So basically this right here and this is basically what we call as transition. So this is transition where we basically go from one state to another state. And we have the input. So this right here is the input, which is basically what we call as the coin. So this is the input. So moving on. The next topic that we have is what we call as a Turing machine. And if you get lost, just remember, it's not a bug, it's a feature. Unless it's a bug, then it's a bug. Got it? But don't try to hack the vending machine. That's just not cool. Unless you're a cybersecurity expert. Then it's cool. Don't worry, it won't get bored unless it's stuck in an infinite loop. And if it gets stuck, just restart it, like your computer or like your browser when YouTube doesn't work. Or unless you're playing against a computer that's been programmed to win. So the next topic is the next topic is what we call as Turing machine. A Turing machine is an abstract computer that can compute anything given enough time and memory. An example of a Turing machine could be a simple palindrome detector, right? So for example, we have the head here, and then we have what we call as the string. Now let's say the head checks for 0 here, and then it checks if we have a similar 0 here at the next end. So basically, it iterates through each string, goes from 0 to 1, and so on. And then finally, it checks if this 0 is equal to the 0. If it's true, in that case, it removes this as it is invalid, and it will also remove this. Next, it again goes to this one, and then again checks and iterates through it, and again checks for the end digit. If both are matching, then it removes this and it removes this. And similarly, again, it checks here and it checks here. It finds a match. So hence, it returns a value of true. So this is a simple palindrome detector, which is a type of a Turing machine. Another task that you can also take a look is that Turing machine increments a binary number. Turing machine can be used to increment a binary number. Next, we have what we call as a RAM model. A simple RAM chip looks as so. So we have CS1, CS2, RD, write, Then you have 87, 128 cross 8, RAM, 8-bit, data bus, chip select 1, chip select 2, read, write, seven bit, address, instructions. The RAM model is a simplified view. Instructions act as registers and memory. It's used in algorithm complexity analysis. So for example, here we have a simple RAM model, which has two chip selects. So essentially what it does is, based on whether it's a 0 or a 1, it selects either of these chips. Then we have a read state. So if read is equal to 1, then basically the RAM model is in the read state. And if write is equal to 1, that means we are writing to the RAM chip. So this is there. And then we have the next, which is basically a 7-bit address for the RAM memory. And this has an output of 128 cross 8, and which is basically an 8-bit data bus output. So it basically outputs an 8-bit number. FSMs are like vending machines. You put in some input and you get a specific output. Unless the vending machine eats your money, then it's a problem. Turing machines are like super smart robots, but they can get stuck in infinite loops. Like when you're watching YouTube videos and you can't stop. RAM is like a computer's short-term memory. It remembers what you're working on, but forgets when you shut it down. Like when you forget where you put your keys. Oops. So next, we have the practice task. Why do programmers prefer dark mode? Because lights attract bugs. FSMs are like traffic lights. They have states and transitions. But unlike traffic lights, they don't get jammed unless there's a bug. Turing machines are like superheroes. So a practice task for you guys is these 3 tasks. First, draw an FSM for traffic light. Next would be to name 3 components of a Turing machine. And the third task is basically to explain a RAM model in 2 sentences. Why do computers make great listeners? They never interrupt. FSMs are like recipe instructions. Follow the steps and you'll get the desired output. Unless you're a bad cook, then you'll get a mess. Turing machines are like geniuses. They can solve complex problems, but even geniuses need a little help sometimes, like a pencil and paper. RAM is like a computer's sticky note. It remembers what you're working on, but only temporarily. So to recap and close, we have some of the following that we had gone through in this lecture. We went through FSMs, Turing machines, and states and transitions. We also took a look at some examples that were key to understanding the problem. So to recap and close, FSMs, Turing machines, and RAM models are abstract ways to understand computation. Next, we'll explore numerical algorithms. Thank you.